Anthropic's Mythos model showed that it can identify more vulnerabilities in critical software than ever before.
Hello, I'm Klon Kitchen, Managing Director of the Global Technology Policy Practice at Beacon Global Strategies. And I'm joining you today as a special guest host for this podcast. I'm pleased to be joined by my colleague, Dr. Divyansh Kaushik, a Vice President here at Beacon, and also a PhD holder in machine learning from Carnegie Mellon. Div joins us today to discuss the rapidly accelerating trajectory of artificial intelligence, its emerging security risks, and their geopolitical stakes. Stay with us as we speak with Dr. Divyansh Kaushik. Div, thanks for coming in and having a conversation about AI. As we get started, I think it will be helpful for the audience, and it will certainly be helpful to me, if I attempt to give a layman's explanation briefly of how we've come to this point. And then I'm going to ask you to help us understand where we are and what's around the corner. So if I understand things correctly, a lot of the original way we approached building AI was a strategy that essentially tried to code these algorithms to be experts in a narrow domain. So for example, if we were building an artificial intelligence algorithm for image recognition, we wanted to be able to recognize cats. An engineer or a programmer would have to go in and try and program all the nuances of what makes a cat, little pink nose, pointy ears, whiskers, fur. And that was quite labor intensive. And of course, there's always tons and tons of details that get missed. And those systems, because of all that, weren't particularly good. Around 2012, we have a confluence of developments. So we have finally a lot of digitized information upon which these algorithms can actually start leveraging. We have some core advancements in the underlying computer science that really helped us understand this idea of what's called neural networks. And then we had some tailored hardware. We had some chipsets, particularly gaming chips, these graphic accelerator chips that allowed compute to be much more efficient and capable. So those three things come together. And that opens up this new approach that had been considered previously, but we just never really kind of got right. And this was the idea of these neural networks. And essentially what that means is you would point these AI algorithms at a large bucket of images, and you would simply tell it, this is a cat, this isn't a cat, this is a cat, this isn't a cat. And the algorithm over time would begin to make its own distinctions as to what are the essential nuances that make a cat from an image recognition perspective. And it actually turned out really good. They started to be able to ultimately outperform humans in image recognition. And then a little bit later, we walk into this world of large language models where essentially, I'm deliberately being simplistic, but where essentially we pointed an AI algorithm at the internet and said, go figure out cats. And it was able to start understanding not only image recognition, but all kinds of other things about cats in general. Now, I know you have a PhD in machine learning. I know I probably just made your skin crawl with those descriptions, but for the normal person out there, does that largely capture this moment? And how would you describe the particular moment that we're in right now?
First, thanks for having me here. I think this will be a fun conversation. So, yes, you did capture it pretty well. I think the way I would describe the current moment is it's weird. It is unlike anything we've seen in decades. This is like you have a thing in front of you, a shiny monolith that came from somewhere. It's glowing. You can see, you can tell what it's doing, but you can't tell how. You can make interpretations. You can try to make it do things, but you don't fundamentally understand how. And you don't currently understand how to steer it to do things, right? So this is very powerful technology where we do not fully understand what is happening underneath. We do not fully understand how to make it do the things that we truly want it to do. And that's the kind of world we are in, where the technology keeps progressing so faster, but our understanding of it still lags so much.
So here,
And
let me stop you there because I think a lot of listeners are going to say, wait a minute, I don't understand. How were we able to build this technology and yet not understand how it works?
right. So the fundamental nature of neural networks is that, as you described, you're providing inputs and outputs. And these are large mathematical operations, a lot of equations that are being solved underneath by your system. And as a result of that, you are able to design a model that, you know, you can give new inputs and it will predict an output. But you don't fundamentally understand how those equations are being solved because in this case, instead of, say, solving two equations or five equations, you're solving trillions of equations. Uh, the data that you're looking at is in multiple trillions of tokens, which tokens is how we describe words. And just the nature of how these models are able to look at what we've given them, identify patterns, but also extrapolate them now. They're not just doing a rough pattern matching anymore. They're not stochastic parrots. They are able to generate new ideas at times. They're still not fully there, but people have been able to use these models to solve unsolved problems in science and math. Uh, the models of 2012, 2015, even 2020, they were not able to do this. The core thing that has made all this possible is large scale compute, large amounts of data, and fundamental advancements in algorithms. How this big paper came out in 2015 that created this transformer architecture. Then people developed a new method of mixture of experts. Those are very technical terms, but basically that's saying like it's like designing a new engine for your Ferrari. It suddenly starts running faster with the same amount of fuel, the same kind of fuel.
So I want to pick up on that metaphor because I was gonna push in just to try and understand a little bit. It seems like what you're describing is that in the kind of underlying computer science of artificial intelligence, we've actually crossed a threshold where in the past we were building um, more traditional engineering outcomes like an engine where we knew how this part fit into that part. We knew that when you fired it this way, it produced this result. We could describe everything from the actual mechanical interactions, but even kind of the physics behind it all in pretty nuanced detail. But now we've transitioned more into kind of like brain science, where we see individual neurons firing and we see these kind of inputs, okay, sleep, and then outputs, okay, brain recovery in some form or fashion. But describing the connection between those two things just currently exceeds our scientific knowledge. We just can't see that deeply into the operation of the brain to describe that. It sounds like you're saying, yeah, we've crossed into that world on artificial intelligence. We're no longer just doing kind of brute engineering. We've now crossed into a place where there are things happening between the inputs and the outputs that we simply cannot see deeply into and explain.
I think I would say that we crossed into that territory in 2022, and 2023 was the big year when the general public woke up to it, when they were able to access chatgpt.com and were able to see how these models are performing on all the everyday tasks they were putting them to use for. Then you started seeing much better models come out. Remember, like 2023, when ChatGPT came out, people were using GPT 3.5. We are at GPT 5.5, roughly 3 years later, less than 3 years later, actually. Uh, and the capabilities that we see today far exceed what we saw even in 2023, let alone in 2025, actually. The models we saw in 2025, there's this meme on the internet of Will Smith eating pasta, how you see the model generating images over years improving so much because partly the models have started to understand real world much better, the physics much better. They've started to understand language more deeply, the inherent concepts that we describe in language more deeply. uh, there are things that we humans just assume as tacit knowledge that models are now able to get at by more experimentation. And so we are in this age where the most powerful scientific labs in the world are not government run or operated. They are in the private sector.
Yeah, so we're going to pull that string quite a bit in just a second. But before we start talking about what's around the corner, I want you hinted at it a moment ago, but I want you to unpack it just a little bit more because it will feature prominently in the rest of our conversation. So you mentioned these kind of key pieces of infrastructure that are enabling this technological growth. What are the things that feed artificial intelligence innovation and growth, and how do they kind of fit into broader conversations about national power and national security?
Yeah, so there are a couple of things. One, amount of compute you have access to.
Okay, when you say amount of compute, what do you mean?
So the in high NVIDIA, AMD, Cerebrus GPUs that you're talking
Okay,
about.
GPUs are graphic processing units, super special AI accelerating chips.
Exactly. So GPUs were originally designed for gaming, but what they're really good at is a lot of mathematical operations in a very short amount of time. A CPU takes a long
A
time to do
central
the same.
processing unit, the old form of.
Right. Which you still have like some combination of in your data centers and whatnot, but that takes a longer time. GPUs just parallelize those mathematical operations. That's why they were so powerful in gaming. What a lot of machine learning models are doing essentially underneath is a lot of matrix multiplications. And so GPUs are very well designed for that. And they can do those multiplications faster at scale. And when you're looking at trillions of equations to be solved, the more GPUs you have, the better of a model you can train.
Okay, so because of the growing gaming industry in the United States and around the world, industry said, hey, we need better chips to be able to process these highly realistic visual uh, games. And so they created GPUs. The AI research industry said, these things are really good at doing multiple things at the same time. I wonder if that might help us with AI. So they plugged it in and turns out, oh, yeah, this was really helpful. In fact, it exponentially grew um, AI's efficiency and capability, essentially. And so now the chip industry has focused on these, what we'll call AI accelerator chips, GPUs. And now it's turned out that not only are GPU chips really helpful for building AI, but there seems to be a scaling law that's holding where the more GPUs you have, the better performing the AI can be.
Yeah. And think of the amount of GPUs you have as like the amount of time you have to think. If you're trying to solve a hard problem, if I only give you 5 seconds, you may come up with an educated guess. It may be wildly off. But if I gave you 5 hours to solve a hard problem, you'll get better. If I gave you 5 days, you'll get even better. Giving you 5 years probably gets you even better, or like you are able to solve much harder problems. That is what we are doing now with the amount of GPUs that say OpenAI or Anthropic or Google DeepMind are deploying to train their models, and then to do this new kind of model serving called reasoning models, where when you ask a model a question, the model goes back to think. And what it is doing is it's trying to spin out a lot of chains of thought of how it would solve that problem.
All right, hold on. We're going to go down that road, but I want you to come back to the essential pieces that enable AI. So you've talked about compute. Anything else?
Data,
Okay.
obviously, like the more data you have, the better representations you can learn of the world of physics, of whatnot. Uh, there's talent. There are very few people who know how to make this thing work. Uh, there's energy. Obviously, you need the power to power these data centers. If there is no energy, like I can have all the GPUs in the world, I can't put them to use.
Yeah, you can't turn them on. Okay. Okay. So those are the kind of key elements that are enabling AI. We'll come back to that in terms of how that features in geopolitics. But so you got compute, you've got energy, you've got talent, and you've got data. All right. So now you were starting to unpack reasoning models, which goes to the question I wanted to go. Is like, okay, so we know how we got here. We have a basic understanding of where we are now. What is around the corner? What is this moment of inflection that we're facing? And again, speak to us like we're intelligent but ignorant.
Right. So, like when I was saying in 2023, people got to see this for the first time. When they would put a query to chatgpt.com, it would immediately put out an output. That was an instantaneous output. From there on, labs have created this new paradigm, which they internally call post training or reasoning models. What happens is the OpenAI started this with O1 model. If you query the model and you say, you pose a very difficult question, the model takes time to think, uh, colloquially speaking. But what is happening in the backend is it's trying a lot of different approaches. It is going to the end state for each of them, and it's seeing which one works and which doesn't. It backtracks if it thinks it has made a mistake, then tries another thing. And so basically, that is how we solve problems. It take the more time a model takes to think, the more better its output is likely going to be. That is how the correlation has worked out so far, and that is partly what we are seeing in the cyber domain today. The kind of conversation we've been having for the last several months in DC and around the world with Anthropic's Mythos model, it has been that the model is so powerful that it can take like really hard problems of identifying vulnerabilities.
Okay. So we find ourselves in this moment where these models are now reasoning. They're actually quasi thinking about a topic or an issue or a challenge or a question along multiple lines, making these determinations as to which of these lines makes the most sense and most accurately delivers the resolution or the response that the user intends. And it can explain how it's done that as well. And that's why they call it kind of reasoning. Okay, got it. So now we're in this world where we have reasoning models, which is itself a massive leap forward from where we began, say, in 2023. But I know from our conversations, you think that we're also at a moment of another kind of step change potentially in terms of how models are developed. Talk to me a little bit about what that is, why you think we're in this moment, and if we are in this moment, what that might mean.
Yeah. So over the last several years, the AI research community has been thinking this way that, okay, AI models are getting really better at doing a lot of tasks. and perhaps even better than humans on several of them, which is what we call a jagged frontier. That in some cases, the models are better than humans, in others, they're perhaps not. Uh, and as models get better over time, with newer training runs and more compute, more data, people have started to use models themselves to identify new architectures that future models should have. And so we saw this with Google DeepMind came out with Alpha Evolve. And that was like the first time we saw hints of what we call recursive self improvement, which is basically using an AI model to train a better new AI model. Now, we're not at the stage where you don't need humans yet, but we've started to see that AI models themselves are able to do a much better job at identifying architectures, creating training pipelines, identifying what data to use to train better models, the next generation. OpenAI used this in Codex 5.3. An earlier version of Codex 5.3 was used to create the final version of Codex 5.3. Now, the theory goes like this. If models can do better than humans on most tasks right now, over time, we anticipate that given how these models are getting really good, especially at formal tasks where they're closed, the task is not vague, there is a clear end state that you can look at, that perhaps models will get much better at doing AI R&D itself. And there have been lines of research on this for several years, like neural architecture search is one of that. But this is just like a fundamentally different approach where models are not just trying to identify the best architecture, they're trying to identify the whole pipeline. And the idea is that, say, in 2 years or so, if you talk to people in the labs in Bay Area broadly, they will say that by March 2028, they think they can develop models that will autonomously be able to develop better models.
All right. So let me try and say back to you what I think you're describing as this moment. AI is increasingly getting better at lots of things, but things like coding, because there are kind of very clear rules and kind of logic chains, AI has always been good and is getting particularly good at that kind of work. So much so that it is increasingly operating for longer and longer periods autonomously as it does programming type work. The research labs have taken that reality and said, well, okay, let's point that at AI development itself, which is a kind of engineering and coding, of course. And let's see how good these systems do at essentially building themselves. And what we're seeing is not only are they performing at a higher level than we anticipated, but they're improving at a faster rate than we anticipated. So much so that if everything holds, that we are entering a world where AI systems will be able to effectively build better AI systems almost, or eventually perhaps even completely autonomously. Is that what you're describing?
That's exactly right. And there are a lot of things going on here, right? Like, this is not just specific to coding. This is about any formal task. And most of STEM is that
All right. When you say STEM,
science, technology, engineering, math, right? Where computer science is one part of that, physics, broader mathematical problems, where you're seeing unsolved mathematical problems that for like centuries that are now being solved by these models. And that's the difference between those more formal, closed tasks and, say, coming up with a new theory of justice or something, where it is like philosophy is not a closed formal task. And so models are getting really good at those closed tasks. And we're like, okay, That is the way we can use to do better AI development itself. And the to your point, the curve of progress is getting steeper, much steeper. There is this curve by this organization called Meter, Model Evaluation and Threat Research. It's a nonprofit out of Bay Area. They do independent testing of the models on long horizon tasks. And they have been tracking the length of software development tasks that these models are able to autonomously complete with 50% reliability and with 80% reliability. For years, they've been doing this. The trend you see is that every 7 to 8 months, the task lengths that models are able to complete, both with 50 and 80% reliabilities, those double.
Okay, so autonomous AI systems are doubling in a matter of months. So they're literally exponentially growing in capability and the time length in which they're able to work autonomously.
Yeah. And so right now, you have models that can do multiple days of software development work autonomously with 50% reliability. By November or so is the expectation that you will be able to get to roughly 4 days of task length with 50% reliability. By next year, we will be looking at models that do multiple weeks of tasks with 50% reliability. With 80%, like we're still like dealing in hours rather than days. But given the exponential, we are not far enough from this becoming a days, weeks, months problem.
Okay, so let's just stipulate then that this kind of growth is occurring and is going to continue. What does that mean in terms of what are the implications of achieving this moment where AI is now building itself? Well, I often hear this term thrown around in these conversations about takeoff. What is the opportunity? What is the concern?
So I'll start with the concern first. One of the concerns with current models, even current models, and we've had this concern for a while, is steerability of the models. To get the models to actually do what we intend to do. It's the King Midas problem.
Explain.
So the king asks that everything he touches turn to gold, but he didn't literally mean to be like, if I touch my daughter or my family members, that they turn to gold and die. So you define an objective for these models as well. But sometimes the models end up doing something else altogether to be able to achieve that objective. If it means that achieving the objective requires jailbreaking a cyber system, that is perhaps not the intention, but a model will try to do that because you haven't told the model what is good, what's not. And we have been making a lot of progress on that. This is the alignment problem. And you're trying to align the models that you're not just solving for rewards, but you're trying to do it in alignment with human values and like whatnot. So Anthropic has this Claude Constitution, the sole document of the model and whatnot, where they're trying to instill those values and constraints in the model on how to do things. This reasoning paradigm that we talked about, that is another way of like putting alignment in place that you're able to trace how a model thinks about a problem. So whether it did something that it should not have done, and you can penalize the model or give it reward signals to either double down or not do that.
All right. So we don't want these things. We don't want to say, hey, optimize paperclip production, and it conclude that the best way to do that is to kill the whole human race.
Correct.
Got it. Okay. So what's the takeoff challenge? What is that?
The takeoff challenge comes with when you achieve full recursive self improvement, let's say, hypothetically, we get there. even if it's not March 28th, say by 2029, we get there. But we haven't fully solved the alignment problem or the steerability problem. The rate of progress is so fast that we are getting so many things thrown at us, so many problems. The models are able to use real world strategies, thinking 20 steps ahead of us where we don't fully understand. And we can not solve that alignment problem they're on, which is the takeoff. And that is the time we have to solve most of the technical challenges, if not all, to the extent we can on the alignment.
So takeoff is this moment where AI is now training itself and it has sufficiently progressed in the sophistication of those models that it's building autonomously that humans are no longer really able to understand even many of the inputs. And so, maybe we can see the outputs, but we don't just not understand what's happening in the black box in between, but now we don't even understand some of the originating decisions and choices in code that went into building this thing. So we're just kind of falling further and further behind in our ability to understand the capability. That's the risk.
That is the risk. The opportunity is also endless. You are able to identify new scientific solutions, better cures of things, because you can conduct billions of simulations with newer, better technology. You can create a digital twin of the human cell and run a lot of medical treatments on it and design new drugs. You can solve unsolved problems. We can look at how does the human race explore beyond anything we have in space. Like those kinds of problems and those opportunities open up.
We're going to take a quick break and we will be right back with more of our discussion with Dr. Divyansh Kaushik.
Beacon Global Strategies is the premier national security advisory firm. Beacon works side by side with leading companies to help them understand national security policy, geopolitical risk, global technology policy, and federal procurement trends. Beacon's insight gives business leaders the decision advantage. Founded in 2013, Beacon develops and supports the execution of bespoke strategies to mitigate business risk, drive growth, and navigate a complex geopolitical environment. With a bipartisan team and decades of experience, Beacon provides a global perspective to help clients tackle their toughest challenges.
We've done some kind of heavy lifting, kind of setting the ground of understanding this moment, how we got here, what this means. And I think what you just concluded on is the fact that this emerging technology is here. There's no rolling it back. There's no getting rid of it. This is a thing that we now have to confront and deal with. And with this technology comes very real risks that we're going to talk about, but also very real opportunities. And those risks and opportunities essentially extend into every domain: economic, social, political, certainly defense and national security, which I think that sets the stage then for a conversation about how AI is now shaping geopolitics. So let me take a stab at kind of setting the frame there. So right now, I think it's safe to say that on the advancing science of artificial intelligence, the United States enjoys many benefits. We are still the most attractive place in the world for the talent to come and participate in this endeavor. It is American AI labs that are pushing the frontier of all this. It's American companies who we think of as being the kind of the instigators and drivers of this innovation. The hardware, even though much of it is actually manufactured within the sphere of influence of China in Taiwan particularly, the design of those chips is done by U.S. companies. And so we're able to really be driving the kind of bleeding edge of the hardware side of this as well. And we have currently a great deal of compute. We also have some challenges. But the essentially the only other participant in the race at this matter that matters is China, and they enjoy many benefits as well. So, well, you tell me what are some of the benefits that China enjoys as they try to realize the many benefits that we've been discussing with artificial intelligence?
Yeah, I think one of the biggest benefits that China has is they have no shortage of talent. They have no shortage of data. They have a lot of really, really good engineers who have been able to identify ways to develop models under constraints that the United States has imposed on them. And I think some of those constraints, like we should have doubled down on early on. But right now we see labs like ZAI. They recently came out with this new model called GLM 5.2. That model, tested by independent evaluators, comes up in top five globally. I think China has a lot of issues it will have to deal with over the next 2 years. But right now, they are pretty much at the frontier along with American AI labs. They are developing really powerful models and making them open source. They're just pushing them out to the world. Use these however you want. Here they are for free.
So, real quick, do you think that the capability race on the frontier between the United States and China is really like essentially it's a tie right now?
It's not necessarily a tie right now. There is a pretty big gap. So GLM 5.2,
Wait, what is that?
the model I was just talking about from ZAI, that model, American labs released comparable models last year. So there is like a 9 month gap between American labs and Chinese labs
On the cutting edge.
on the cutting edge. Now, you don't necessarily need the cutting edge for all the problems. Uh, Most of the problems we want to solve for can be solved by the 10th best model. So China is doing a really good job at diffusing these models. They have been deploying them across the economy. They have been putting them in healthcare and their financial sector, in universities. They have been leading in the development of the robotics sector, which I think will be the next frontier to take AI from just being a digital technology to also interacting with the physical world.
Okay, so you're describing two races then. You've got the first race of the bleeding edge of the technology itself, and the US has many advantages in that regard and maybe enjoys something in the neighborhood of a 9 month lead. Okay, got it. So that's good news. But then you're describing a second race, and this is this race of diffusion, of kind of pushing artificial intelligence out as broadly as possible into the economy and into the world. And that's a race where the Chinese are doing very well in the sense of they're making many of their models freely available, calling open models. They're kicking them out and they're either free or cheap. And so, if I'm understanding you correctly, is the risk that the US has exquisite models, but they're expensive and unavailable. And then the Chinese could have very capable models that are cheap and very available.
It's very similar to the smartphone problem. American companies do not own majority share in the global smartphone market, but they do have majority of the smartphone revenues. Chinese companies, they own the global majority. In especially in like the global south, they are overwhelmingly popular, but barely any of them make any profit. And so that is the kind of situation we find ourselves in with AI as well, where American companies not really being utilized by everybody around the world, very exquisite models, $200, $250 a year subscription, APIs costing people tens of thousands of dollars a year. Whereas the Chinese models, they're not making profits. They're probably making losses, and what they're focused on is capturing the global market.
And so if they capture the AI global market the way they captured mobile phones or telecommunication networks, okay, what does that mean? Why is that a bad thing if it is a bad thing?
I think it's not necessarily a bad thing right now, but it could become a bad thing. There are a lot of reasons why we want to have trusted vendors in our software supply chain. And one of the reasons, but there was this research that happened a year, 2 years ago, that you can embed what we call sleeper agents in these models. Say, year 2026, the model will respond perfectly fine on certain queries. But when the year is 2029, the model will shut down or just start sandbagging itself,
What do you mean by sandbagging?
where it dramatically drops its performance intentionally. And so you can embed those sleeper agents in the models. There are no clear ways to get rid of them right now. In research, people haven't made a whole lot of progress. So that is a concern.
So, okay, so if the majority of the world, including US businesses potentially, decide to orient themselves on open, cheap Chinese models, one of the risks that they are embracing is this idea of sleeper capabilities and ultimately throttling of the capability itself. So you become dependent on the Chinese model, but then we know that because of the way the Chinese government works, they could quite easily influence the performance of that model, even shaping the outputs that it's able to generate. Is that what you're saying?
Yeah. And you're seeing signs of that even today, where you see if you use Chinese models to do coding tasks, if it thinks that you're an American, if the Chinese model thinks you're an American, it introduces more vulnerabilities into the code than if it assumes you're a Chinese national. It introduces even more vulnerabilities if it thinks you are a US government official. So a lot of startups in the Bay Area are using all these open Chinese models to do their coding tasks. And that is a big risk that exists today. The sleeper agent risk is a potential risk that we won't know until those sleeper agents are activated. But there are real risks with relying on technology which you cannot trust.
Okay, so this is yet another extension of the broader challenge of unsecure data flows and unsecure supply chains, right? This is just the AI version of that flavor. So, I will often say that an immutable reality that we now face and have faced for almost 2 decades is that securing nations means securing networks, and securing networks means securing supply chain. And that's just an unavoidable reality. And that's how we find ourselves in conversations about foreign derived AI models, but then also GPU export controls as we're trying to put a governor on how quickly our chief pacing threat in Beijing is able to develop AI models and the like. Okay, got it.
And it's not just about developing the models. GPU controls are also slowing them down in diffusing the models.
Explain.
So if I have Einstein's brain, would I like a million of them or would I like 100 of them? If I can deploy millions of Einsteins across the United States, I can solve a lot more problems. If I only have 100, I have to prioritize, I have to triage. Right now, China's national champion in chips, Huawei, they are not able to scale their chip production. They cannot produce enough chips. So, one, their chips are lagging NVIDIA's, and two, they cannot produce enough. So, they are barely able to meet domestic inference demand.
What is inference?
Inference is when you query a model, when you're deploying these models. So, that just means people are not using AI for like very creative, out of the box challenges that people are able to use in the US. And that is also very critical as technology becomes more mature. For instance, if China had access to all these chips and was able to deploy the models freely across industries, we know they are already way ahead in manufacturing than us. If you deploy powerful AI models in your manufacturing industry, which is already ahead of the United States, there is a possibility that that industry then reaches an escape velocity where the US manufacturing sector is just never able to catch up. So there are a lot of reasons why we want to make sure that the US companies have all the compute that they can get. Right now, if you hear CFOs of all the American labs or major execs, they will say they cannot find enough compute. They're they're leasing chips that were manufactured in 2022 because they cannot get enough of it.
Okay. So in our last couple of minutes, then I want to move the conversation into the core discussion of national security particularly. So what I would love to hear you describe first is what are some of the obvious ways in which AI already and will continue to inform and shape American national security capability? What are the kinds of things that the US is using AI for, and what are the kind of doors that it's going to open up for us going forward?
Yeah, I think there are a lot of ways we're currently using it. I think one of the things to think about is how it really helps in solving kinds of logistical challenges. You have millions of constraints that you're trying to solve for. You don't necessarily know. That is practically the challenge that the military is facing with logistics. And that is one of the ways we're deploying it. One of the other ways is just like ISR, intelligence, reconnaissance, right? Like how you're able to go through billions of images that all the imagery that you've collected to be able to identify what's happening rather than just have a human eye. I think those are like traditional defense examples, but then there are other areas like we briefly touched on Mythos, where Anthropic's Mythos model showed that it can identify more vulnerabilities in critical software than ever before. It identified vulnerabilities in software we thought was perfectly secure for decades. It identified bugs that that have not been identified for 30, 40 years. And so that is a key challenge, both from a preparedness standpoint, but also from an offensive standpoint that we can deploy. It can help us secure our defense industrial base. It can help us secure the code bases in our government systems. It can help us modernize the code bases too. Remember during COVID, we were having all this conversation. Look, how many unemployment systems or how many government systems are in COBOL or Fortran where we do not have the people? Well, these models are really good at converting that into secure modern code.
Got it. So, I mean, my understanding of this is that there's essentially no element of the national security function, just like the broader economic reality, that isn't going to be perhaps decisively shaped by this technology. And with it come all the attendant opportunities and the risks, and we're in the middle of those conversations. So I think one of the big questions that I want to end on is going back to a point you made previously, and that is that the labs in which this technology is originating, these are not government labs. These are not, super secret, high powered, Los Alamos kind of secret kind of capabilities out there in the US government world. These are private companies leveraging private capital to develop these capabilities initially for commercial applications. That then means that the US government is now rendered a national security stakeholder and is no longer the national security stakeholder. And that also means that these private companies now have, whether they intended to have them or not, national security interests and responsibilities. And if those two things are true, then we essentially have a renegotiation of the social contract. How do government and industry work effectively together on these issues going forward?
I think what you said is spot on. Yeah. This is one of the most fundamental technologies that we have developed. It is basically, we are creating a capability multiplier. It is intelligence deployed at scale, where a problem would take one human brain 10 years to solve. You put millions of AI agents to solve in a few seconds. And so no problem set will be untouched by this. How do we actually govern it as the government is a national security stakeholder, not the national security stakeholder, is going to be an ongoing conversation. It is not going to be a one-off thing where we pass a law or issue an executive order and we're like, okay, done, our job's here, good. What will need to happen is the government will need to build a lot more state capacity to be able to understand the technology, because right now that expertise lives in the private sector. The government will have to establish channels of intelligence sharing with these labs, because these labs are going to become just as important parts of the defense industrial base as the US government itself, where foreign adversaries will want to steal their intellectual property, which they are already trying. They will try to infiltrate. There are the usual risks that these companies will have to face, and then these heightened risks that nobody is really prepared for right now. I think more people are prepared than the rhetoric suggests, but we're just not prepared enough. And the current administration has taken an approach of trying to work with industry on these issues, where a recent executive order tasked NSA to work with these companies on evaluating their models, benchmarking them. I think that's a good first step. We are going to have similar conversations on just like broadly securing the labs, securing their intellectual property. Who has access to critical systems in these labs? All those conversations will have to happen, but I think we're going to take one step at a time, mostly because the industry is not mature enough yet to be able to have those conversations at scale. The other thing is just the threat vector will continue to update. Right now, we're having this whole conversation on AI and cyber in the government. 4 months from now, we're going to be talking about AI-enabled bioweapons. As we were talking about recursive self-improvement, in 2 years, we'll be having that conversation. How does the government prepare itself to be able to rapidly stay up to date rather than just responding to a crisis as it emerges will be very critical here.
Yeah. It seems that there is no way that I can perceive where the US government is able to unilaterally reassert itself in this innovation cycle, like the energy, the resources, and the expertise. It's all in the private sector. Even if you tried to nationalize it, there's all kinds of, points of friction there that would, arrest the innovation cycle and do real damage to the capability development itself. And so both industry and government must continue to become, one, committed to an ongoing conversation. Nobody can just kind of get up and walk away from the table. And two, just embrace the reality that this is going to be bumpy, right? Our constitutional system wasn't built for efficiency. It was built for stability. And we as a people have made a decision that we don't want to live in a country where the government comes in and unilaterally takes action on industry. But we also don't want to be living in a country where industry exercises inordinate control or influence over the government. And so we have some built-in friction, and that's design. That's a feature, not a bug. But it also means that this conversation can really only play out one way, and that's through this iterative, patient process. And so then the only question really becomes, can we go through that iterative, patient process quickly enough to keep up with the technology? And that is very much an open question, and perhaps something we can come back to on a future episode of this podcast. But in the meantime, Divyansh, this has been extremely helpful. Thank you for taking the time. And we look forward to maybe doing this again soon.
Thank you for having me.
That was Dr. Divyansh Kaushik. I'm Klon Kitchen. Please join us next week for another episode of NatSec Matters.
NatSec Matters is produced by Steve Dorsey with assistance from Ashley Berry. NatSec Matters is a production of Beacon Global Strategies.